Because just like in pre-calc, we have to like justify why we have to find zeros and polynomials and stuff like that. Same thing here. You could just say, if I wanted to find the maximum of a function, I could like outsource it to a computer. But my great hope for you, friends, is that you will be the people who design the computers someday. So, right, I need you to know what's under the hood. Okay. So, also, of course, as usual, the theory is important and beautiful, my friends. Okay, let's highlight that. And of course, the AP exam. So that's kind of not a very fun thing to appeal to, but there's something else I was going to say about that. Oh, it's also true that if you wanted to find something about a general function that didn't have numbers in it, you could assert something about it as well. For example, we proved that for a parabola, we proved the other day on the board, a couple weeks ago, that the minimum value or maximum value of a parabola happens at negative b over 2a using calculus, right? Because the derivative is 2ax plus b for any parabola. Set that equal to 0, solve, you get x equals negative b over 2a. So there, it's general enough that you know, maybe we care about general results too. Oh, you don't care. Okay. Absolute extreme values. By absolute maxes and mins, I think you know what we mean by that. Or either, sometimes we call them absolute extrema, because we like Latin sometimes better than English or something. So I think those are words you understand, so we just want to talk about like the calculus angle on those words, because I know that those words are even introduced to you and maybe even back as far as Algebra 2. Think about absolute and global maxes. Or mins. So this is one thing that might have been lost on you in a pre-calc course or something like that. But extreme values can either happen in an interior point or an endpoint of the function. So here are a few very brief examples. So for example, y equals x squared on the entire real line has, of course, an absolute minimum. There is no absolute maximum. What about x squared, though, on a different domain? So this is the function defined on this interval. What about that? Absolute min? Yeah. Absolute max? Yeah. And you can say what they are if you like, but the absolute minimum is 0 and the absolute max is 4 on that interval. It's worth mentioning that really every function, like remember that, right? Every function really, even though this hasn't been an emphasis in pre-calculus, every function should be handed to you together with its domain, right? Especially as we think about like the real world, you know, we have to kind of limit our understanding of a function to where it might be applicable. What about this interval? Looks very similar to the last one. What's the difference? And is there an absolute max or min? What's the picture going to look like? Very similar to the last one. Yeah, there's only a maximum, right? If we're defining it on this like half-open interval. So yeah, no absolute minimum. There is an absolute max. Of course, we can do the same. Another similar thing. We can do both endpoints, and then there's neither. Is that cool? So, all right, now we're finally ready to after seeing these pictures, I don't know, when can we guarantee that there's an absolute maximum or minimum that it will achieve, that a function will have both? What do you think? What's the condition for the extreme value theorem? When it's defined on something? Look back at the 4 examples we just did. What did you say, Ashley? X value has a y value. Every what? Closed interval seems to be important. We're not going to focus on even power. Closed interval, what do we require? Not just that it be defined on the closed interval, but that it be the same criteria for the intermediate value theorem. Continuous on the closed interval, right? Continuous on the closed interval, then it must be the case that the function achieves its maximum and minimum value. But notice that if you relax the constraints a little bit on those last 4 examples, we see that that's not the case, right? It'd be easy to construct counterexamples to this. So notice on this first one I have here, we have some function defined on a closed interval, say. And notice on that particular example, we have the maximum and minimum both achieved, and they both happen to be interior points, right? What about this function? We have a function that's continuous on a closed interval, but there the max and min happen to be endpoints, both of them. Or you could have something like this, where the maximum value happens to be an interior point, and the absolute minimum happens to be an endpoint, right? So any of those things can happen. I just want to make sure you're aware. And I just think that it's so often true that we hand you a picture like this, and you forget to, or this, and if we ask for maxes and mins, I don't know why, but endpoints is just like gone out of your mind or something like that. It is maybe a new discussion for calculus, for our class, for us to be so fixated on the endpoints, right? But those are part of the analysis. As we move forward into like optimization problems of various kinds in the real world, you'll have like some, I don't know, fuel efficiency function or something like that, and maybe we want to minimize this function, and we just need to recognize that the minimum value might occur at one of the endpoints. Okay. Of course, you've heard this term from your pre-calculus experience as well: a local maximum or a local minimum is the maximum on some open interval. So I don't know, I think you've done this kind of before. So what makes this point right here a local minimum? It's clearly, the way I've drawn this picture, it's clearly not the global minimum. But, and I'll come back to this picture in a second. But if you were to take an open interval around this x value, then it would be the smallest value in its neighborhood. By neighborhood, I mean some open interval containing that x value. If you can find an open interval containing that x value for which the y value is the lowest, then that's a local minimum. So, I don't know, work through these here, just shout them out. What's this one here? Yeah, it's both, right? What about this guy here?
Local max.
Just local max. Shout out this one.
Local minimum.
You can read. Good job. What about this one?
Absolute.
Yeah, both.
And oh, sorry.
And this one? Yeah, you've done this before. Okay, so one thing I put on this picture just to emphasize how these things could happen is, I don't know, we should start thinking about the calculus here too, which we haven't done in previous years. In previous years, you've kind of just been like, well, the highest point or something like that. But what produces for us a max, min, or extreme value in general here? Here, Jack, first.
I have a question.
Go ahead, ask the question.
What open interval could the endpoint be on with the minimum?
Yeah, so it's on the real line, not defined by the function. So if this is, so we're asking if it's the largest value in its, so it's not defined in part of that interval that's satisfied vacuously, right? But is this the lowest? Is there some open interval of real numbers containing the x value of this point for which the y value is the lowest? Yes. Yeah, in fact, any interval, any open interval containing that point will do. Does that make sense? So let me draw one there. Do you have the same issue with this local minimum? Why it's local minimum?
No, because like that's the end, right? Like
Yeah.
don't you need something on both sides for it to be in the open
Yeah.
interval?
So yeah, why is this a local minimum? So let's say this is x equals 5 here. So we just need some open interval of real numbers such that any open interval you like.
It doesn't have to be like part of the domain.
It doesn't have to be part of the domain, right? Such that the y value that goes with x equals 5 is less than 4 equals. Well, depends on how it's defined. Less than f of a for all a in the interval I. This is called the interval I. So you could say from a minus a number to a plus a number or something in that interval, right? Sorry, from 5. Right.
It's like it's technically like if it's undefined, like you just
Yeah, and like, so if f of one of these numbers is undefined, then it's satisfied. Yeah. Do we use the word relative extreme before in your life? That's another word too. Okay, so all right, I'm ready for your comment, Ashley. So what do we think is required from a calculus standpoint to have a max or a min of some kind?
Things around it are in the opposite direction.
Okay, yeah. So now maybe we care a little more about that. I mean, I'm trying to think if you have opposite direction. What do you mean by that?
Around a maximum, things are lower than it.
Okay, all right. Can you talk to me about, in particular, derivatives? Yeah.
Well, it seems to me that every max or min either has a horizontal tangent or is at a point where it's not differentiable.
Yeah. So in fact, we intentionally put one of those in this picture, just so that you wouldn't think that it's only horizontal tangents we're looking for. Over here, we have a point of non-differentiability, right? So notice that can happen on either one. Yeah, Rosie?
Where the derivative of rate of change changes sign.
Yeah, and the reason, and this is kind of a little bit what Ashley was saying too, where the derivative changes from being positive to negative is like an important observation. It's not like, I don't know that we would say that's sufficient if the function isn't defined there though, right? That would be the only thing, right? Like 1 over x squared changes from increasing to decreasing, and yet there's no maximum at all on the function 1 over x squared, right? Even though it changes from increasing to decreasing. So we would also demand that it like be defined there. Yes. 1 over x squared goes from increasing to decreasing. 1 over x squared doesn't have a local max. It doesn't have a max at all. All right, so this is just what, so these points, now we should say too, is it guaranteed that if you have a place where the derivative is 0, that you get, I mean, think of what's your classic go-to example of a function that has a derivative of 0 and yet doesn't have a max or min there? Yeah, x cubed provides a nice example of that, right? At the origin, y equals x cubed, nice horizontal tangent, but doesn't have, it's not a max or min. So this is the first thing, I think this is sometimes called Moz Theorem. The first thing to say is if the derivative is defined and you have a max or a min, then the derivative better be 0 there. If the derivative is defined. Notice the implication doesn't run the other way. I just want to make sure we're highlighting that. Right? If the derivative is 0, it might be a max or min. Check. So that's this place and this place, for example. And again, I have a note at the bottom. The converse is not true. And then this is what Ben was highlighting, right? We've got two instances where we want to check if a function is not differentiable at a point, or if its derivative is 0. Neither of those things guarantees a max or a min, but those are, we're going to call those critical points, as in places to consider, right? So all of these places are critical. These 3 points here are critical points. The point here where we have a 0 derivative, here and here, and up here where the derivative is undefined. We're going to name all of those critical points of this function. In this particular picture, all of them do happen to correspond to maxes and mins, but that of course isn't necessarily going to have to be the case. But can you think of any function that has a point of non-differentiability where that point is not a min or a max? Jack?
Wait, a specific one?
Yeah.
Like,
Or you could draw a picture.
like one that goes like that.
Yeah, in particular, I don't know, well, yeah, one that goes like that, he says, the vertical tangent or something.
Yeah.
Yeah, do you have a different one, Corinne? Yeah, I was going to say we could use the cube root of x as our go-to function on that. There's no max or min at the origin, and yet that's not differentiable there, we know. The Grace-Inger function, let's not talk about that. I don't know. Well, the reason I hesitate with functions that have piecewise constant intervals is because some people would, depending on their definitions, would say that, like, places where it's constant have places along the way that are all mins and maxes, depending on whether you use like a less than or less than or equal to, you know? But I think most people would say it doesn't have any mins or maxes. Huh? Yeah, right. Like some people would say a horizontal line is like increasing and decreasing. Yeah. Absolutely. That's what your textbook from your pre-calc textbook would say. All right. So I think I've said this already, but it's worth putting on a slide. Critical points are not always maxes or mins, and there are the two examples that you already gave. Look, see, people. Kind of thing that it's dangerous business, assuming the converse. Don't do that. All right, do you need to see that anymore? Is that okay? Yeah. I'll give you another second. We want to show you at least one nice little example before we go.
Class feels like an hour. So slow.
All right, let's take a look at an example of a function. Can we guarantee that this has maxes and mins? Why? Like, is this question even well formed? How can? Is x to the 2/3? What's required? That it be?
To exist.
What's the hypothesis?
Continuous on the closed interval.
Continuous on the closed interval. Is x to the 2/3 defined on the interval, closed interval, -2 to 3? Is it continuous on the closed interval? Right, that's done. Met the demand, so we can definitely ask for this. So we'll say that we definitely can find these, so now let's find them. We will need the derivative. Let's ask about the derivative on this interval. Does it have any critical points? What is it? It's one critical point, namely 0. And why is it a critical point? Because the derivative is undefined. There are no places where the derivative is 0 for this function. But it's undefined at the origin, so that's a critical point. But because it's defined over a closed interval, we're also going to check the endpoints. So The critical point, f of 0 equals 0. The endpoints give these values. So those were the only candidates on our list. Endpoints and critical points. Point. So that's the only list. That's the list of values we have to consider. So let's answer the questions. What's the minimum? What's the minimum value of this function? 0. What's the maximum value that it achieves? I need you to think about which of these is greater, of course. Yeah, the cube root of 9 is a bigger number, even though I haven't evaluated it exactly, or I haven't approximated either of them. So the absolute maximum of f, which we were guaranteed to have, is the cube root of 9. That's the largest this function can be. And it occurs at the right endpoint. Notice this is one of those cases where we have the maximum occurring at an endpoint. The minimum occurs at an interior point for this function at x equals 0. And the minimum is 0. Yeah. Yeah.
I said the derivative has to be 0 for it to be the minimum.
No. The derivative at a minimum will be for, if it's not at an endpoint, will either be a place where the derivative is 0 or undefined.
Oh.
That's what we're looking for. So there's the picture, right? And that captures what we've just said, doesn't it?
Yes.
So what do we do if we're trying to find extreme values? You're going to be faced with, in the homework tonight, you're going to be faced with some functions that are defined on some intervals. So what do? You find the derivative and determine where it's 0 or undefined. Those are your critical points. Then also consider the endpoints and do what we just did. Just figure out which ones are the biggest and smallest. If it really is continuous on a closed interval, then you're guaranteed to have answers to these questions. On the last one, this picture makes me think, if it had been defined on the interval -3 to 3, that would have been fine. What would we say for the maximum? Well, we would say the maximum is still the cube root of 9, right? It just happens, it happens at 2 places though. And that's okay for the absolute max to be, for there to be like a tie, right? The point is there like a value that f achieves for its maximum? And the answer is yeah. The point is.
Wait, but we don't need to find locals for this.
Well, you'll be considering all the locals as you do this.
Oh, so each number you find is a local.
Well, the endpoints are local extremes. The interior points that you find that are critical values that you test are going to be options. Huh? The cube root of, well, at x equals -2, we have a local max, yes. But that wasn't asked in the last one. It just said find the absolute maximum. But you're right. If someone asked you for the local,
That would be the local max.
all right, I think that's all I have, right? So not like we're easing into this. Which one am I going back to? Just this page here. Yeah. We have 5 minutes. What do you want to do?